All right, let's say hello to our next speaker. Ron Yurko is a first-year stat PhD student at Carnegie Mellon. He received his BS in stat from Carnegie Mellon as well in December of 2015. And at CMU, he co-founded with Maxime Horowitz the Carnegie Mellon Sports Analytics Club. Ron previously worked as a baseball operations data and analytics intern for the Pittsburgh Pirates during the 2014 season, as well as a quant analyst in the financial services industry. So let's welcome Ron.
Thank you for the introduction. So just to get started, the current state of football analytics is not easily reproducible. Vast amount of research is done with proprietary data, potentially biased human judgment data as well from charting. The reason this is a problem is because this is hindering the development of a football analytics community, like which we see in baseball and hockey. Because we ultimately want more people involved and we get more insight to the game. So this is one of the reasons why Max Horowitz actually created then the NFL Scraper R package. So you can easily access play-by-play data going back to 2009. And ultimately, you can share your research, share your code, and we're providing more insight into the game. You can access the package through GitHub. And what's actually been really neat is we've seen various blog posts from analyzing Seattle Seahawks to fantasy football sites actually using NFL Scraper package. And what ended up happening was Pittsburgh Post-Gazette writer Liz Bloom did a little article on our package, as well as the current state of football analytics. And being a young, foolish person that I am, I decided to read the comments. It's stats geeks like these that are ruining sports. And of course, the person goes on with various grammatical mistakes, ranting about the fallacies of statistics. Now, another comment, it's actually kind of interesting. Stats don't work as well in football compared to other sports such as baseball. You can't statistically evaluate a running back without evaluating his offensive line. Same thing with a QB. And they go on and end with the platitude, of course, that the only stat that counts is the W. But this is a great comment. They recognize the lack of insight we're getting from raw football statistics. There's many moving pieces in each football play. It's not isolated. We really want to assign credit to each person involved in every single play. And ultimately, from a team's perspective, we need to evaluate players in terms of wins. Wins are directly then related to roster, payroll, etc. So what we decided to do is using NFL Scraper, we introduced our NFLWAR framework for a reproducible way for trying to estimate the wins above replacement for offensive players in football. So the goals of NFLWAR are we're going to properly evaluate every play. We're going to come up with a way of assigning individual contribution to each play for each player. Then we're going to evaluate relative to replacement level. Because ultimately, average players are still better necessarily than maybe 40, 50% of people in the league. So for a team, we want to know how good a player is versus, say, someone that's on the practice squad, our replacement level. And ultimately, we want to convert this then to a win scale. And one of the final things, probably the most important thing, is then estimating the uncertainty in WAR. And we're able to do this to each season going back to 2009. So how do we actually value plays? So the two main frameworks we consider are expected points and then win probability. Expected points, the idea is historically, how many points is a team expected to score given this current situation? Several ways, obviously, to do this. And the other idea, win probability, what's the likelihood of winning the game given the current situation? One common approach, simple logistic regression. And really, our NFLWAR framework can actually be applied to both valuations, but today we're just going to focus on the expected points approach. So how do we calculate expected points? Now, from a statistician's point of view, ignoring point after attempts for now, I look at every play and I can have 7 possible outcomes in terms of the next scoring event. I can have, with respect to the possession team, a touchdown for, field goal, or a safety, or the opponent getting a touchdown, field goal, and safety, or a no score occurring. And then our covariates are simply just describing the situation. Down, the yards to go, field position, etc. So the most common way of doing this is a nearest neighbors approach. We're going to identify similar plays in the data set, and then ultimately we're going to take an average. But what defines a similar play? Are we only looking at the exact same situation? Are we taking Euclidean distance? Are we going to say that the difference between down 1 and 2 is the same as the distance between downs 2 and 3? There's a lot of assumptions that go in here, and a lot of tuning that isn't actually answered. So the next easy approach is a simple linear regression. And this is an intuitive idea. The closer we get to our opponent's end zone, the more points we're expected to score. But is treating the next score as continuous appropriate? So what we have here is for each play, we count then, so the x-axis is the number of plays, and the y-axis then is the next scoring event. And this is with respect to the team with the ball. So obviously we can see that this offense-driven league, 2009-2016, more likely than not, team is expected to score. And what we have here along the y-axis is I also have it spaced out in terms of those actual point values we're associating with each of the events. So for the statisticians in the room, what do you think is going to happen when I fit a linear regression to this? Because if we think about a linear regression model, we need to still hold true to our assumptions of the model. So think back to intro statistics. One of the first things you look at is you check the residual plot. Y-axis, you have your residuals. X-axis, your fitted predicted expected points values. And ultimately, when we look at this, we just want to see a random scattering of points. We don't want any trends. That's just not what happens here. This is a clear violation of linear regression assumptions. We see clear trends in the data. So we can't use this. So natural extension, then, is just to consider this as a classification problem. Logistic regression is not just limited to 2 classes. We can extend it to any number. So ultimately, what we're doing this is we're predicting the probability of each of these possible events relative to the no scoring as our base case. So the important thing is the model is generating probabilities of each of the scoring events. It actually doesn't care what the value of the next score is. So right now, I have touchdown as 7. But really, if I think it's closer to 8, I can maybe change it. Or if I think it's less than 7, I can bring it down. Same thing with the other events. So ultimately, then, to get to expected points, we just take our probability of touchdown, given that it's 3rd and 10 on the 20-yard line, X time remaining, times it by 7, and then we add that up with the other probabilities given the current situations. Then we get our expected points of a play. To then get to an actual value, we look at the expected points added. Simply just the difference between the expected points at the start of the following play versus the current play, expected points added for the play. But for passing plays, we're actually just not limited to that. If we want to get at the idea of how much contributions for quarterback versus receiver, we can divide it up in terms of the air yards. So using the air yards, I know what is the expected points added through the air EPA. Simply just the difference where it was in the air versus the start of the play. And then I have a stupid sounding stat called the YAC EPA, the yards after catch EPA, which is simply just the difference from the end relative to where it was in the air. Still for this, though, how much credit do we assign to each player? If Matt Ryan throws a 70-yard touchdown to Julio Jones, 30 of which the yards were in the air, 40 of which Julio Jones ran for the touchdown, how much credit gets assigned to each? Because obviously one player is not solely responsible for a play's EPA. So in terms of allocating EPA, one popular approach is total QBR. And ultimately, the purpose of this is they're dividing the credit between the players involved in passing plays to get the idea of what's the true value for a quarterback. However, they're using their proprietary manually collected data. So they have a lot more information than what I'm dealing with in terms of publicly available data. Publicly available data, I only know who's directly involved. I only know who's throwing the ball, the target receiver, as well as the defenders in terms of who's tackling or intercepting. But I have some context. I know the air yards, the yards after catch, whether it's left, middle, or right, and I know if the passer was hit on the play. And then for rushing, I only know who was actually running the ball, who made tackles, as well as the run gap and location. So if it was, say, New England left end versus New England left guard, and then same thing on the right side. So our approach then to deal with this in terms of isolating players is to use multi-level modeling. Now, multi-level modeling is gradually becoming more and more popular, and it makes a lot of sense because it's a natural approach for group structure. So what I mean by group structure, for each passing play, I have a quarterback, and then I have the intended receiver. So these are 2 groups. Quarterbacks, obviously, there's fewer quarterbacks in the league in a given year throwing the ball. So we're going to see a lot less variation for quarterbacks than the variation we see for receivers. there's a lot more potential receivers in the league. So there's going to be a lot wider range of values in terms of our receivers. And the other thing is the fact that every play is a repeated measure of performance. So sometimes we're going to see Tom Brady, he's getting the dose of Gronk with the treatment of the New York Jets. Other times he's getting the dose of Gronk with the treatment of the Cleveland Browns, and so on. Maybe he's getting the Brandon Cooks treatment, et cetera. So plays are not independent. Multi-level modeling lets us capture the effects of the individual players. So a popular example of this is actually Baseball Prospectus' deserved run average, where they're trying to get at the true value for a pitcher by accounting for all the individual effects of, say, the catcher, the umpire, the batter, and so on. So as I said, the key feature of this is that we're dealing with groups. And so what we look at here, the EPA line, think of that as just your standard linear regression. We have our beta coefficient. The difference now, though, is we have these varying intercepts for the quarterback and the receiver. So we're using the fact that quarterbacks are a group, and we want to use the information of the group collectively in terms of giving us an idea how far away an individual quarterback is relative to that group average. And same thing then with receivers. So unlike linear regression, we're no longer assuming independence. We're letting the fact that we've observed Tom Brady multiple times tell us how good he actually is. And taking this normal distribution on each of these varying intercepts, using this overall group average, this provides us a way of shrinkage. So now using this, if we only have a quarterback with, say, 3 pass attempts, we're not going to say actually whether or not he's good or bad. He's going to get shrunken towards the average versus someone who has many pass attempts over playing the whole season. We have more information on them, so we know actually how good or bad they actually are. So in terms of then our modeling, what we end up doing is then we take this varying intercept approach to get just a single value effect. And one of the group variables that we're actually able to create for rushing is a proxy for O-line blocking team side gap. I know what the team is, I know which the run gap was, and I know the location. So I can make Pittsburgh left end, Pittsburgh left guard, Pittsburgh middle, and then right end, right guard. And what we ended up doing was we created separate models for passing versus rushing, because we have different group variables. So for passing, I know the possession team, the quarterback group, the receiver, and then the defensive team. For rushing, I have this team side gap, the rusher, and the defensive team. So what we end up doing, we take these varying intercepts, and this gives us an idea of the individual points added. So to make it a trendy stat, it's a lowercase I, and it's named after a beer, IPA. So this gives us an idea then of how well a player is relative to the average in the group that they belong to. And then we can get the same thing with teams, TPA, team points added. And so we have this TPA value for each team side gap in the rushing models. And to simply then get individual players' total points above average, we take their IPA value and multiply it by the number of attempts. This gives us our IPAA. So for the rushing models, what we actually do is we have 2 models. We're separating QB versus non-QB. Because the idea being here is non-QB are designed rushing plays. And then we adjust for the rusher position as a non-group variable. For QBs, we're including sacks as well as then with the idea with the design runs and scrambles. And so we're replacing the team side gap, because we don't always have this for QB runs, with just the offensive team. So now we get our IPA rush estimates as well as then our TPA rush side gap estimates. Now what I'm showing here gets back to what I was describing in the intro about multi-level modeling. What we're looking at is we have the 3 group terms, our opposing defense, rusher, and team side gap. The important thing here is the level of variation in these groups. We can see that rusher and team side gap have similar amount of variations, wide amount of variation relative to the opposing defense. So if we look at actually like the top side of the team side gap, those are the teams that are well above the red line indicating the average. So the top team side gap last year was Buffalo middle. And this is actually interesting because the bottom 5 team side gaps were all middle for something like San Francisco, Jacksonville. Very bad teams last year, obviously. And then for rusher in the top right, we had Mike Gillislee, Jay Ajayi, Le'Veon Bell versus the bottom players like Matt Forte. But the important thing here is this difference in the variation versus, say, the opposing defense. Because all of these 3 groups, they're accounting for each other in the model. So we're getting Le'Veon Bell's effect while accounting for the effect of, say, the Cleveland Browns and where Le'Veon Bell is rushing. So a similar idea then for the QB model. We can see the level of variation for QBs with respect to their offensive team and then the opposing defense. Now what we have here, this x-axis is the sum of those 5 team-side gap TPA values. So as I said, I have a TPA value for Pittsburgh left end, Pittsburgh left guard, Pittsburgh middle, right end, right guard. So the x-axis, I'm just summing those together to give us kind of an idea of their total efficiency. The y-axis, I'm taking each of those individual pieces and multiplying it by the number of attempts to that respective side gap. So what I can see is I can see which teams are overperforming and underperforming with respect to their total efficiency. So Pittsburgh, for instance, the sum of their 5 pieces is positive. But because they ran more to a negative side, their total value is actually negative. Total meaning worse than average. And then the overperforming side, New England, the sum of their 5 individual pieces was negative. But because they ran more to the positive side, their total value was positive. Now, this isn't necessarily a total valuation offensive line, because ultimately this is just the direction of a run. And as we know, teams, various blocking formations, players in movement, et cetera, left end rush might not actually just be behind the left end, right? So this is just an idea, though, of how they're doing their rushing plays. For a passing breakdown, we could just use expected points added as a response variable, but we want to take advantage of the air yards. So what we end up doing is create 2 separate models for airEPA and yards after catch EPA. And what we have here then is both models take all pass attempts, where the incomplete passes for both models are using for their response just the raw EPA value, because this is then stressing the importance of completions. And both models adjust for the QB's hits, the receiver positions, as well as the location, because on average, plays have a higher expected points added over the middle of the field. And the yards after catch model actually also adjusts then for the air yards as well. And what this ends up giving us is we get our IPA air and IPA yak estimates for every player. And so going back to the initial point I made, we can see here now for the airEPA model, we have our 4 groups. But because there's so many more receivers in the league than, say, quarterbacks, we see a mass amount of variation for receivers in their intercept values relative to QBs. So this is telling us the fact that we just have so many more, so we're going to have a wider range of possible values. So in the tops of the receivers, we have players like, for airEPA, Mike Evans, right? And then in the bottom, shouldn't be surprising, Tavon Austin. And we see similar results then for the yards after catch model as well. The same sort of variation between the receivers versus the quarterbacks. So then, similar idea from before, what we can do is on the x-axis, I have that yak EPA value, IPA value for each of the quarterbacks versus their air yards IPA value along the y-axis. And important thing here, going back to the idea of the shrinkage in the middle, that's where our average group is densing at, where the 2 lines are intersecting, the 0, 0 values. And what you see in here, you have very average quarterbacks such as Ryan Tannehill, and then players that have very few attempts last year. They're getting pulled towards the average. And then we also see then the difference for players that have short but accurate throws. Positive yards after catch IPA, but negative air IPA, such as Alex Smith, Sam Bradford, versus then the gunslingers like Josh McCown, Sean Hill, Jay Cutler. They're not accurate necessarily, so their yards after catch IPA is negative, but they can throw the ball far. That's where they can provide value. And then Jared Goff was at the bottom of both last year. He's obviously improving. And then the next step we want to do is evaluate this relative to replacement level. So ultimately, right now, we're taking a very similar approach to NFLWAR. We're finding replacement level based on the rosters. So each team, we find for each position and sort by the number of attempts, and we do this for both receiving and rushing. So to get an individual player's IPA total, we simply take each of these individual points above average values for the rushing, the air, and the yards after catch to get their total points above average. Then we create a shadow replacement level player by taking the average of the replacement level players for their IPAs, then summing over, we multiply them by player I's number of attempts to give us then what the replacement level player would have done given if they had the same number of attempts of our player of interest. So then we simply take the difference between the two to get player I's individual points above replacement. Now, to get this to wins, we're actually taking an idea from a CMU stats freshman last year who did a project with Sam Ventura on looking at the relationship between the regular season wins for a team and their score differential. So what we're looking at here, we could see this the clear linear relationship. We also view it by season. So if you think back to your linear regression class, the interpretation of a coefficient for each 1 unit increase in regular score differential is associated with a blank increase in regular season wins. So to get to 1 win, we just take the reciprocal of that coefficient. So after fitting the line, our points per win is just 1 divided by this coefficient value. So for instance, in 2016, this coefficient value is 0.0319. So that equates to roughly 31 points per win. So to finally then arrive at WAR, we take our individual points above replacement and we divide it by the points per win. So for some results, in 2016, what we're looking at here is the top 5 and bottom 5 QBs by WAR. And they're sorted by WAR, and I also have the individual pieces, the air WAR, the yak WAR, and the rush WAR. So shouldn't be surprised, Matt Ryan last year was fantastic. He led the league in WAR 4.07, but actually his rush WAR was negative. Versus then other QBs, Tyrod Taylor might be a surprise at number 2, and then Cam Newton at number 5. But this is really stressing the fact that relative to average, Cam Newton is providing so much more value from his rushing and mitigating the damage from sacks than, say, other QBs that are not as mobile. And then at the bottom, even though Jared Goff had, say, necessarily the worst intercepts, Eli Manning, because of the number of attempts, was the most costly quarterback to his team at negative 2.23 wins above replacement. And we look at a similar thing then for running backs as well. Last year, Le'Veon Bell was the most valuable running back in the league, 1.87 wins above replacement. And interestingly, we could see the difference between him and David Johnson. David Johnson's rushing WAR is a lot smaller than the others in the top 5. But David Johnson as a receiver is incredibly valuable. And then we can see something for Ezekiel Elliott. He actually has negative air WAR. And similarly then for Jay Ajayi, negative yak WAR. And then we can see how they compare to the bottom 5 with Matt Forte at the bottom. For tight ends, we actually have another interesting thing going on. Top 5 kind of consists of guys who are getting their WAR in the air. Think of end zone threats. But Travis Kelce, the number 1 at 2.53 wins above replacement, he's providing so much value after the catch. And we can compare this, of course, then to the bottom 5 as well. Probably the most interesting one is wide receivers. So the number 1 wide receiver last year was Mike Evans. All of his value is coming from through the air. He actually was negative WAR after the catch. And then we have players like Brandon Cooks and Odell Beckham, who are very balanced receivers with respect to both. Then on the bottom 5, we have Tavon Austin as negative 1.46 wins above replacement, but he actually did have a positive rush WAR value. Now, this isn't to say Tavon Austin is a terrible wide receiver, but maybe how he's implemented is poor. This also gets back to a point I want to make. So DeAndre Hopkins is in the bottom 5 in 2016. DeAndre Hopkins is in the top 5 in 2015. Now, with publicly available data, I don't know how bad a throw actually is. So the Brockening happened last year, right? And the ball was sailing who knows where. So relative to the year before, DeAndre Hopkins' completion percentage was his reception percentage was just terrible. But I don't know that with this data. So he's damaged by that. But going forward, that's something to keep in mind in terms of the stability of these metrics. So just to recap, we're properly evaluating every play with the multinomial logistic regression model. And multi-level modeling provides us with an intuitive way then for trying to estimate an individual player effect. And this actually can easily be extended if we know every player on the field at every time. If I'm a team, if I know the personnel package, I can control for plays, etc. I can get the individual effects for all of these things. But ultimately, it's kind of naive to assume that the player is going to have their average effect on every play. Tom Brady's not going to be the GOAT on every play. Maybe one day he doesn't drink enough water and he throws some passes like Josh McCown, some other passes like Joe Flacco. So we really want to get at the uncertainty in the different types of these IPA values to generate then intervals of WAR. And we also need to refine our definition of replacement level. Right now, we're really we're just looking at this roster idea, but maybe I could consider like clustering of usage of different players, whether they're down-specific players or players specific to yards to go. But that's for another time. So here's a self-promotion for the Carnegie Mellon Sports Analytics Conference, which is coming up October 28th. Registration will be up soon, and I encourage everybody to check it out. Great lineup of speakers. And I just then want to thank Max Horowitz for all of his work creating NFL Scraper, Sam Ventura for advising every step of the way, Jonathan Judge at Baseball Prospectus, he's a great guy and answers all questions, and then also Rebecca Nugent and the rest of the CMU Statistics Department for encouraging this kind of research and all their instruction. With that, thank you.
We do have time for a question or two before we break for lunch. Are there anybody with questions out there for Ron? Always tough to ask questions when lunch is on.
I didn't hear. So not yet, but that's the next step what we have to take, like the stability, because that's one of the most important things, right? But not yet.
Last question.
So you showed results for team side gap. Have you thought about doing a rusher side gap as well to see if certain players were better to either side or up the middle or to tackle versus guard?
That's an interesting idea, and I'll keep that in mind going forward to look at, yeah.
Talk to your co-op about it.
Okay.
All right, thanks everybody. It is time for lunch. Let's thank all three speakers or all three groups.